Welcome! This video we're going to use the sketch, organize, solve method to solve momentum problems. So with a momentum problem, you've usually got a very interesting incident, an explosion, a collision, something like that. And we want to look at the times before and after it instead of really during the times during it. So our first thing when we sketch is we want to draw the before and after states of the event. And we want to do just before and just after, not many seconds before, many seconds after. We want to limit it to just as close as we can to that. And then we want to draw an interaction diagram for the during. And when we do this, we can then see if we can justify. We want to define a system such that we can either say that there are no external forces or that there are small external forces we can assume away. This is our impulse approximation. So if we can do this, momentum is conserved because we have force external is 0, which means that the momentum of our system doesn't change with time. So in our organized step, if our momentum is conserved, then we can write conservation of momentum. So we can write momentum of 1 initial plus the momentum of 2 initial, so on and so forth, is equal to the momentum of 1 final plus the momentum of 2 final, and so on and so forth. If we need to, we can decompose into x and y if it's needed. Now, if our momentum is not conserved, that means we have some external force to the system, which means we have some external impulse to the system. So we have the external impulse J external, which is equal to the integral of the sum of our external forces integrated over time. And this is equal to the change in the momentum of the system. So we're going to use one of these two equations to figure out what we have. And then as we're doing this, we want to write a table of knowns and unknowns. And we want to see, as we're looking through the problem, see if we have a collision type. So our collision types are inelastic. If we're inelastic, we are saying that the final velocity of 1 is equal to the final velocity of 2 is equal to the final velocity of 3 is equal to some final velocity. If we have an explosion, we are saying for the explosion that all of our objects are actually together. So we are saying that the initial velocity of 1 is equal to the initial velocity of 2 is equal to the initial velocity of 3 is equal to an initial velocity. If we are saying that we have an elastic collision, we are saying that the kinetic energy initial is equal to the kinetic energy final. And what we can do is we can look at the elastic solution and use that in our solve step instead of having to redo the elastic solution every single time. So in our solve step, we want to apply our collision type equation and then solve the conservation momentum equation. So that's if a normal thing. If we happen to have elastic, what we first need to do is we need to transform into a frame where V2I is equal to 0. If we do this, then we can use our elastic solutions for V2I equal to 0. Our elastic solutions are that V1F is equal to M1 minus M2 over M1 plus M2 times V1I. And V2F is equal to 2M1 over M1 plus M2 times V1I. And then what we would use is then we need to transform back into the original frame. So go back to videos about Galilean relativity to remember how to transform into Galilean frames. But this is how we use the sketch, organize, solve method to solve momentum problems.